Global data generation from AI model training is currently outpacing the capacity of modern hyperscale computing facilities. The internal mechanics of a magnetic hard disk drive rely on packing bits onto a two-dimensional platter. We are approaching the physical limits of how many magnetic sectors can occupy that surface area. Maintaining these planar systems at scale requires a continuous increase in energy consumption, in cooling infrastructure, and physical floor space. Holographic data storage, or HDS, utilizes the entire three-dimensional volume of a photosensitive medium rather than just its surface. Expanding into the third dimension provides the only physical volume left for data centers that have already exhausted the density of 2D storage media. Recent publications from Chinese research institutions suggest they have developed optical systems capable of petabyte-scale storage. The primary barrier has been the hardware. Historically, holographic systems required high-precision optical alignment that was too sensitive and expensive for commercial data centers. However, recent breakthroughs shift the problem from hardware alignment to software-defined AI. Neural networks are now performing the tasks once handled by complex lenses, but this research exists alongside a manufacturing sector that has yet to produce a market-ready drive. Emerging hardware markets also face regulatory scrutiny following high-profile cases of technical misrepresentation and financial inflation. To understand the viability of this technology, we have to look at the specific optical physics and how they compare to current commercial prototypes. Standard holographic recording involved modulating the amplitude or phase of a laser beam to encode digital data. Researchers at Fujian Normal University recently integrated polarization as a third independent property of the light field. Using polarization as a distinct information channel triples the data density within a single page, allowing for 27 possible states per pixel. This multidimensional modulation is achieved using a single, phase-only spatial light modulator. This double-phase strategy shapes the beam into a complex interference pattern. A single modulator design removes the need for multiple light paths, reducing the potential for alignment errors during high-speed operation. This directly contrasts with earlier systems that used multiple modulators, which often failed due to low signal-to-noise ratios. By increasing the amount of information stored at each volumetric coordinate, the physical storage capacity per square inch increases. Encoding more dimensions into the properties of light allows for a higher capacity than is physically possible on a 2D surface. The challenge of reading this data is that standard CMOS sensors only measure light intensity. They are completely blind to the phase and polarization states where the extra data is stored. Retrieving those hidden dimensions usually requires a complex hardware setup called an interferometer. The recent Chinese approach replaces that expensive hardware with convolutional neural networks. AI now processes raw intensity images to extract the encoded data. The tri-decode net uses two intensity images to reconstruct the original 3D data grid from what appears to be random diffraction noise. To assist the neural network, researchers use genetic algorithms to encode data at unequal phase intervals, producing diffraction features the AI easily distinguishes. This mathematical precision brings bit error rates down to levels required for enterprise storage reliability. Trading complex optical hardware for deep learning algorithms lowers the component cost required to build and maintain holographic drives. The storage medium itself is a photopolymer called PQ/PMMA. This chemical matrix must be sensitive enough to record data, but stable enough to prevent it from degrading. The Shanghai Institute of Optics and Fine Mechanics recently improved this medium using nanoparticle doping. Tests on these doped polymers showed a 5.5 times increase in photosensitivity and a 4-fold reduction in volume shrinkage during the recording process. Adding electron accepting molecules to the matrix helps shield the stored data, preventing accidental erasure when the media is exposed to UV light. These stable photopolymers are manufactured into blue-tinted optical discs, which can be stored in standard library enclosures. While the chemistry is proven in laboratory settings, manufacturing these nanoparticle-doped materials at scale is the next requirement for commercialization. There is a gap between academic petabyte claims and the hardware produced by firms like Zijing Storage. Zijing's current prototypes offer 1.5 terabytes of capacity on a 120mm disk, with read and write speeds of approximately 1 gigabyte per second. These devices are third-generation testbeds used for research, not market-ready drives available for enterprise data centers. Verifiable exports from the Chinese sector currently consist of raw materials, such as lithium niobate crystals, rather than finished holographic storage systems. Capital markets are also cautious. The Shanghai Stock Exchange strictly penalizes storage firms that misrepresent technical progress. The case of Amethystem Storage, where management was imprisoned for inflating revenue, proves that a portfolio of patents is not a viable product. For now, global hyperscale centers are not being disrupted. The holographic supply chain is still largely confined to the laboratory. Holographic memory is not intended to compete with the high-speed solid-state drives used for active processing. Its target is the archival storage market, currently dominated by magnetic LTO tape. This technology fits into China's Eastern Data, Western Computing initiative, which requires long-term storage for massive national data hubs. Passive holographic media requires zero electricity to maintain data integrity, unlike the continuous power draw of spinning enterprise hard disks. A media lifespan of 50 to 100 years also removes the need for the 10-year data migration cycles common with magnetic tape. The goal of HDS is to reduce the energy and real estate footprint of the massive datasets used to train future AI models. Replacing hardware interferometers with AI-decoded intensity mapping is a verified scientific transition. Analysts should monitor the standardization of holographic interfaces, rather than expecting an immediate commercial product launch. As traditional media reaches its physical limit, volumetric storage offers the capacity required to house the massive datasets generated by the next decade of AI development.